weekend? Reasonable, good weather.
Awesome.
We've got more cold weather coming, but we'll get there.
Still warmer than a few weeks ago.
Yeah, it's definitely more warm days than cold days. All right, any questions from last time? Anyone started thinking about the 30-point project? A little bit? Okay, I got to talk more about it later today. And that's not going to be due until a week from today, because I'm going to give you a pretty good idea how to get going on it, more than I wanted to do in the actual write-up. Good job on the 5-point homework, halting question. Everybody that I looked at this morning had gotten the right answer and had defined the halting problem and correctly identified that it's a problem that cannot be solved in the general notion of solvability on computers. It's 906. Talk about that in a minute. So the halting problem, the basic statement of the question is, can you write an algorithm or a program that looks at another program and tells you whether it runs forever or whether it stops at some point? And you and I can certainly do this with a short program if you limit it to a 3-line C program. Pretty much any program you look at, you can analyze it and say this runs forever or this will stop at some point. But in general, to write a program that can do that to another program is not possible. And the reasons why are related to what we're going to talk about for the first part of this class today. That should bother you, the fact that someone tells you there's a program you can't write when you can do it yourself. I mean, anything that you can do, you should be able to get a computer to do, right? That's what programming is about. It's getting it to do what you do faster and better. But in fact, you can't write a program that solves the halting problem. And personally, I find it annoying, but apparently it's true. Okay, 907, so I'm back to telling the truth now. So prior to 906, I made this statement. Every statement I write between 906 and 907 will be a lie. And then a little after 906, I made this statement, I am lying. Okay, analysis. This statement true or is it a lie? Well, this was verified by an independent party beforehand. This is an absolutely true statement. Okay, every statement that I was going to write on the board between these times would be a lie. So this must be a lie. Okay, because I wrote it between 906 and 907. But if it's a lie, and my statement was that I was lying, I was telling you the truth. Right? I said I was lying. In fact, I was lying, so it was actually a true statement. But of course, if it was a true statement that I was making, and I told you that it was a lie, then I was lying to you. And so that statement was actually not true, but it was a lie. But since it was a lie and I said I was lying, of course I was telling you the truth, so that statement must have been true. Right, and we could do that for the next 45 minutes. But you get the idea. Determining whether that statement is true or false, you can't answer that. It's in some sense a meaningless question, but it's not. I mean, it's perfectly valid to say, am I telling the truth or am I telling the lie? I think every statement that someone makes, you could assess one way or another, truth or lie, true or false. But I've created a situation where you can't do that with this very simple statement, I am lying. And this is a form of something called diagonalization, or sometimes Cantor diagonalization. It was developed by a mathematician named George Cantor to study certain paradoxes in set theory. And it's very similar to what happens when you try to prove, when you try to construct a halting problem solution. I'm going to give you some other examples that will make a little clearer what's going on here. But it's all basically this I am lying paradox. This was used in an old Star Trek episode to overpower some androids that had taken over the ship, by the way. Okay, let me ask you a question. How big is infinity?
Greater than what?
Greater than?
Greater than what?
Greater than 1, that's true. It is greater than 1. How much greater? And when we talk about the infinite, we use this in our common speech. Newspapers use it all the time. How big is it? I mean, it's really big, right? It's...
Well, it depends what kind of infinity you're speaking of to begin with.
Okay, that's where we're heading. Okay, so let's look at some infinite things. Okay, if we look at the set of all integers, okay, whole numbers, 0, positive, counting numbers, negative, counting numbers, right? That's an infinite set. And we think of it as being infinite because it's bigger than any number that we can think of. Okay, there's more than 1 million numbers in there. There's more than 1 billion numbers. There's more than a Googleplex numbers. There's no bounds to it. That's another way to think of infinity, unbounded. But as you pointed out, we can ask, is infinity always the same as infinity? Okay, so I is a set of all integers. We can think of another set, E, which is a set of even integers. We'll include positives and negatives. So they both have a lot of elements in them. But does this one have more things in it than this?
No.
Why not?
Because you always make a window of the
Okay, and that's a good way to see if two things have the same size. Can you find an association between everything in here and everything in here? And in this case, you can. If you take every number here and multiply it by 2, you get one number here. If you take any number here and divide by 2, you get one number here. So as you said, there's this one-to-one correspondence between the elements in this set and the elements in this set. So we can think of them as being the same size. Okay, and in fact, mathematically, integers and evens and odds all have the same number of elements. And the term mathematicians use is cardinality. It's a fancy way of saying size. Okay, what about fractions, rational numbers? Any number that's an integer divided by another integer.
That's countable too.
That's what?
You can create a one-to-one function from integers to rational.
Right.
They're both countable.
They're both countable. They both have the same number of elements as the integers. Because any fraction can be written as a divided by b. And so you can make all of your fractions right, you can write all your fractions in a table like this, and you can number these. You can start here and move to this number and come down, and go across and go up and over and come down. And you can work your way through this whole two-dimensional matrix of fractions and you can associate each fraction with whatever step it is along this twisting diagonal path. And that'll give you a mapping between integers and fractions. So rational numbers have the same number of elements as integers. Okay, what if you go beyond rational numbers and you look at real numbers? Do you know what irrational numbers are? Like square root of 2 can't be written as a fraction. That was discovered around 500 BC, I believe, and someone almost got off for it. Pythagoras had a cult of people, and they believed in the sort of beauty of whole numbers. They thought everything could be represented as numbers and as fractions of numbers, and that this captured the whole purity of nature and existence. And they started to discover that there were these things called irrational numbers that could not be written as fractions, and this threw their whole sort of mythology into disarray. And one of the members of this cult started publishing some of this information, talking about it, sharing it with others, and the other group members basically took him out on a boat and pushed him overboard to try to keep him quiet. Okay, so this is disturbing stuff. Numbers that can't be written as fractions, such as the square root of 2. There are also numbers that, so square root of 2, if you write an equation like x squared minus 2 equals 0, what's the solution to that? Well, it's just this thing that we call the square root of 2. Okay, that's a definition of the square root of 2, if you like. It's the thing that makes this equation true. There's numbers where you can't define it as a solution of an algebraic equation. Okay, they're not algebraic numbers, they're called transcendental numbers such as pi. You can't find an equation in polynomials that has pi as its solution. So there's a lot more numbers than just rationals and integers. And the question is, if you look at the set of real numbers, are there more things in there than there are integers? And the answer turns out to be yes. So there is at least one infinity that's bigger than the set of integers. So R is a set of all reals. Now, how do you show that there's more reals than there are integers? This was shown by George Cantor, so surprisingly, it's going to use Cantor diagonalization, and it's going to be very similar to the halting problem. So suppose that those have the same number of elements. Okay, then you can find a one-to-one map from every integer to every real number. Okay, so let's start writing these things down. 1, 2, 3, 4, 5. These are the integers, and these are the real numbers that somehow we've magically mapped to this set of integers. So this is 2.75136 something. This is 4.12611. This is maybe just the number 3. This is the number 17.1717. And this is pi. Okay, and you can keep filling this table out because you've given me this one-to-one mapping. You've told me these are the same size, and so there is some sort of mapping here. And every real number will correspond to exactly one integer, and every integer corresponds to exactly one real number. That's a one-to-one mapping. Okay, so you turn this in for your homework, and I'm going to take this and I'm going to give you a new real number. What I'm going to do is for the first digit, I'm going to look at the first digit of the first number, and I'm going to add 1 to it. I'm going to write down a 3. And for the second digit, I'm going to go to the second number, look at its digit, I'm going to add 1 to that. I'm going to get 2. And for the third digit, I'm going to go to the third number, pick its third digit, add 1 to that. The fourth number, I'll do 1717, make that an 8. And the fifth number, I'll go 1, 2, 3, 4, 5. That's a 5, and I'll turn that into a 6. And if I had a 9, I would just turn it into a 0. And I'm going to keep doing this. And I'm going to get some new number, x. So what integer corresponds to x? There's a one-to-one mapping between reals. This is a real number. some integer must correspond to x. What integer would it be? Well, it can't be 1 because the first digit is different between x and the number that maps to 1. It can't be 2 because the second digit is different. It can't be 5 because the fifth digit is different. It can't be any number n because when I look at the nth digit of x, it'll be different from the nth digit of this number. There's no real number anywhere in this table that has this value because of the way I've constructed this number. Okay, going along this diagonal and changing it, I've taken the situation and I've thrown a little twist in at the last minute, and I've deliberately forced a situation where the original assumption, which is that every integer corresponds to at least one real number over here, that assumption comes back and haunts you. And it basically turns on itself and introduces a falsehood. And so this is the way that Cantor showed that the number of reals is bigger than the number of integers, that you can't have a one-to-one mapping. And because you go along the diagonal, it's called a diagonalization technique. Okay, now for the really, really annoying part. So this is a really big circle. It contains all the integers. Yeah?
Wouldn't it be easier to just argue that the reals are larger than the integers because you never have a finite interval over the reals?
If you know what a finite interval is. I don't know when topology came around, but yeah, I mean, that's basically the topological argument. True. Okay, so big infinite circle containing all the integers, bigger infinite circle containing all the reals. Okay, and this infinity is fundamentally bigger than this infinity. So, a natural question to ask, is there some set in between those two? Is there some set that has more numbers than the integers, more elements than the integers, but fewer than the reals? Can you find something in between? And it doesn't have to be a set of numbers. It could be a set of functions, a set of sets. It could be anything. Okay, but is there some set whose size, whose cardinality is strictly in between that of the integers and that of the reals? And it was imagined that the answer is yes, we just haven't found it. And this is called the Continuum Hypothesis. Okay, and it says that there is some set. Sorry, the Continuum Hypothesis says there is no set with cardinality between the cardinality of I and the cardinality of the reals. If you have more elements than you have in the integers, then you have at least as many as you have in the reals. It's a continuous jump in cardinality. And so this was a question that was posed beginning of the 20th century. David Hilbert posed a set of questions that he thought were significant enough in mathematics that mathematicians should pursue these. I think there were 20-some questions, I don't remember exactly. And this was one of them, the Continuum Hypothesis. Can you prove that there's no set with cardinality between here and here, or is there in fact some set that lies in between? Okay, most people thought that this was true. People worked for a considerable amount of time trying to prove it. Nobody ever found a proof. And nobody ever found a set in between here and here. What someone did prove, though, is that you cannot prove or disprove this statement. Okay, it's an undecidable statement. It may be true, it may not be true, but you can't ever decide. And that should be annoying to you also, even more so than the halting problem. Because you have a mathematical system, and here's a simple statement, and you're being told there's no way to prove it or disprove it, ever. No matter how clever you get, no matter how advanced your mathematics gets, you can never find a solution to this one way or another. And there's some disturbing consequences of that. For example, that tells you you're never going to find a set with cardinality in between that of the integers and the reals. Because if you found such a set, then you would know that this was false. And it's been proven that you can't show that this is false. So you're never going to be able to find a set.
Although it might exist technically.
It might exist technically, because if that was enough to prove that it didn't exist, then you would know that this was true. You would have proven it true, and you can't do that either. So it's like the truth is out there, but it's inaccessible to you. And it's not even like peripherally accessible in a way that would let you know what the truth actually was. And that's a fairly disturbing result. And there is still a little bit of debate about it, and it sort of depends on how far you get down to the foundations of mathematical reasoning. There's some wiggle room in there, but generally it's considered to be undecidable, just like the halting problem is undecidable. You can't tell whether this program is going to stop or run forever. And in the 30s, I believe, there were people such as Whitehead and Russell who were trying to formalize mathematics. They were trying to come up with a very rigid definition of arithmetic. And you can go online. Wikipedia has copies of some of their papers. If you look at one of their manuscripts, it's somewhere around page 130 something, I think. They finally make this statement, and they've proven it after 130 pages.
Were they trying to like derive it all from logic?
Yeah, they were trying to start with very, very simple axioms, not assuming this, not even assuming I don't think that A equals A. Trying to start with very, very simple, basic axioms and work everything up from that and formalize mathematics. And they were eventually able to prove that 1 + 1 = 2, and so on and so forth. And they were trying to get a very rigid understanding of arithmetic. And then someone named Kurt Gödel came along and ruined their day. And he basically proved that in mathematics, there are always going to be questions that you can never prove or disprove. There's going to be undecidable questions. Or you're going to have so many basic assumptions that you're going to have contradictions. So either your system is consistent and there's undecidable elements in there, there's questions that can't be shown to be true or false, or you've added enough axioms, enough basic truths to prove everything, but you've also added too many, and you're going to find contradictions, such as the I am lying paradox. And so it seems to be an inherent problem with, I don't know if it's with the way human minds work, or if it's something fundamental with existence, or what, but there seems to be this sort of basic problem with knowledge and information processing, where you mostly seem to end up with these simple-sounding questions that can't be answered one way or another. Okay, and that's what the halting problem is about. It's a computer science implication of this incompleteness. And that was actually one of the elements that went into the mix in the creation of the cell matrix idea. Was trying to do introspection from outside yourself. Because the whole problem with the I am lying issue is you're making a statement about the statement you're making. Okay, this is a problem in set theory. A lot of the paradoxes that come out in set theory are because you start talking about sets of sets. And once you talk about a set containing sets, you can talk about a set containing itself. And so this whole kind of introspection, self-analysis seems to lead to these undecidable issues. And one way to possibly get around that, and at least one person suggested this in the homework, was by using more than one algorithm, having more than one element, by trying to take your analysis and somehow move it outside the system and look back in on itself. And that's basically the idea of cells being able to analyze other cells, and the idea of having cells be uniform so that the thing which is doing the analysis is the same thing as what's being analyzed. Okay, so that's not on the exam. But that should bounce around in your heads a little, and we'll come back and talk more about it in another lecture. But just sort of food for thought right now. Okay, engineering-wise. Long homework number 3. Okay, so it's not due until a week from today, because I'm going over some of the details today. I bumped it up to 30 points instead of 20 because it's a pretty ambitious assignment, but I think everyone here can definitely do it. If you don't get all the way to a complete solution, there's still a lot of stuff you can do on the way, and there's a lot of points in there, but I think everybody can get it all the way through to the end. And Friday, I'm not going to lecture on new material. Again, I'm going to do this as kind of a lab instead on Friday, so I'll be here with a laptop if you want to come in and work on your homework, if you want to ask questions, if you want to show me where you're at and what you're stuck on, anything like that, and I'll be here Friday during class time for that. If you have general questions, I can go over them on the projector. Because I'd like everybody to be able to do this. And as I said in the assignment write-up, this question is sort of like pure cell configuration. This is something you can't do on any other device right now. You can't take a Xilinx Vertex device and make a circuit that will read truth tables from one set of blocks and transfer them to another. You could do it if you get into some funky JTAG programming and you need some lawyers because you have to do some reverse engineering and stuff like that. You could probably do it, but it's not very intuitive. It's very cumbersome. In a cell matrix, it's actually a very intuitive, straightforward process. The engineering that goes into making the circuitry is a little convoluted, but the actual way to read truth tables and transfer them is very straightforward and sort of canonical. So it's a good assignment to work through anyway. And the problem was basically draw a small matrix here. The problem was basically you wanted to copy the truth tables from some cells. And somewhat arbitrarily I said, let's go to the second, or row 2, which is the third row, 2, 5, all the way out to 2, 8. And these are your source cells, and you want to copy them to 6.5 through 6.8. You want to read those truth tables and replicate them down here. Okay, there's a lot of ways you can do this, but I'm going to get you started on at least one way to go about it that should be fairly straightforward. When I was like 10 years old, my brother and I had this statement, the barbaric way is the efficient way. We say it in Latin. And it works with cell matrix. Think like, just get in there barehanded and get the matrix to do what you want to do. Don't be bashful about it. Okay, so we need to build some wires to read these truth tables and some wires to be able to write these truth tables. So let's be lazy. Let's just start those wires right here and right here so that they're going to end up right where we need them. We'll put the PC on top so that the target cells are going to be directly next to the cells we're trying to read and the cells we're trying to write. Okay, so that's one thing you're going to need. You're going to need a pair of wires that'll move from 3040 7080. Start them on the west so you're moving in the same direction as these cells are laid out. So you're going to need some sequences, okay? And I think the wire building classes are sufficient for building these sequences. So you don't need to be defining those funky cells that actually make up the PC and the CC. And you're going to build wires that move across to here and over to here in sort of the usual way. So you're going to have a target cell here for this wire and a target cell here for this wire. But you're going to have to transfer truth table bits somehow. So my recommendation, and I did this on Saturday, just to make sure it worked. works. So build some wires, which will reach over to the beginning of these regions of cells. And then 2, load a binary circuit. What you're really going to want to do is you can read bit values from here and send them back along the program channel. You need to get those into this program channel, send them down, and load them up in there. And with a regular program channel, control channel cell, you've got information going back and forth between the 2 channels for the sake of communication. So once you have a wire started, you want to rewrite what these cells are and just make them straight wires. And there's nothing wrong with doing that. Okay, this can be an actual PC and CC cell. This can be a PC and CC cell. But in the leftmost column here, these can just be straight wires. Just take the data from the west, pass them to the east. And then add whatever you need to do your transfer of truth table bits from the source to the destination. So take the bits coming in from here and send them down. And down here, instead of a straight wire, let's make an OR gate. So we can get bits from either the west on the regular program channel line, or we can get them from the north. And then let's make an AND gate. Which takes what's coming in the west and the north and ANDs it and puts it out here. Okay, this is like a transfer signal. If you put a 0 in here, then all you have is just a straight wire going across. You have a straight wire going across and these bits coming back are ignored. When you put a 1 on the transfer input, now whatever's coming back along this program channel will get ORed with what's coming in on this program channel and get sent down the wire. Okay, so when you want to actually transfer a truth table, you turn on the transfer line, you set a 0 to the program channel on the destination, and your bits coming back here will go down into this target cell. Okay, and you can go into the loader and you can write the circuits for this leftmost column and just make yourself like a 1x9 circuit or 9x1 with the right wiring and logic in there. And then to actually use this, configure the source target cell to read a truth table. Configure the destination to write a truth table. So, how do you write a cell that will read a truth table from the north? What does it have to do? You gotta put a control. Look to the north to put that cell into C mode. Data. Alright, data comes in and I'm going to send it out to the west so it goes down the program channel. And remember, these program channel lines are actually bidirectional. So data will come back. And if you want a non-destructive read, you can also take this and send it back up into the north. Okay, so that's the source target cell, the destination target cell. Is slightly simpler. You put the cell to the north in control mode, you take the data coming down the program channel from the west, and you just send it out to the north. Okay, so that's basically what you need to do the homework. Make sequences to have 2 wires, create a binary circuit, overlay this transfer circuitry on place, and then make sequences to do this configuration of the target cells. Turn on the transfer line for a clock cycle, so that'll copy this cell to this cell. Then extend the wire 1 step, reconfigure the target cells for the source and destination, turn on the transfer bit, read the next truth table and copy it in, and so forth. Okay, there's some technical details to actually doing all that, but that's the basic program. So if you take a stab at this by Friday, like I say, you can come in and if you have specific issues or questions with it, I'll be happy to talk to you about it and help you figure out what's going on. But it's a good assignment to do, not only because you get 30 points, but you end up with a pretty unique circuit in the end. And this is, you know, this can be the building block for a lot of different dynamic circuits. This is how you can build a hardware library where you read pieces of circuitry from some pre-existing store and create new circuits on the fly. It can be how you do fault handling, where you have a copy of your circuit stored somewhere, and when a circuit fails, you can pick up a copy of it and move it somewhere else. It's sort of a building block for a lot of dynamic circuitry in a lot of different functions. So it's a good circuit to be able to put together and work with and be familiar with. All right, any questions on that? All right, so I'll stop there. On Wednesday, I'm going to go back to something that we talked about just before break and just after break, which was this notion of lookup tables and the possibility of a physical lookup table, this question of using a scanner to compute sines and cosines. We're going to look at that and discuss a different version of a self-configurable system, which would be a continuous valued cell matrix. And its values, its inputs and outputs are going to be real numbers instead of ones and zeros. And its truth tables are actually going to be infinite things that can store all possible mappings from inputs to outputs. And we'll look at sort of the basic design of that and some of the implementation details and some of the ways we would use this. And we'll go from there. All right, that's all. See you on Wednesday.